let's talk about three different algorithms that are lesser known in WebRTC and Voice over IP. Before we begin, we need to understand the audio processing pipeline that we have in WebRTC and in other Voice over IP solutions. So it all starts with a microphone. We have the microphone and the person is going to speak towards the microphone. We capture that raw data and then we pass it into an encoder. The encoder is going to compress that information. Once compressed, it is going to send it towards the network. In the network, it goes to the other side. We don't really know how. It gets there magically over Ethernet, IP networks, whatever. And then it gets received on the other end. The receiver on the network, again, knows and understands WebRTC and the processing pipeline. It knows that it is receiving audio. From there, the audio itself or the compressed data is going to go into the decoder. The decoder will decompress the data back to similar to the original data that got captured on the microphone, and it's going to be played back into the speakers. So that's how media processing pipeline works. This is a very simplified version of it, but it is enough what we're trying to do here. I want to start with one algorithm that we should all know, which is acoustic echo cancellation. After that one, we're going to go to the three others. In acoustic echo cancellation, what we're trying to do is to take the audio that comes out of the speaker and goes into the microphone and remove that. Otherwise, what we're going to have is echo on the other side. Why? Because everything that I hear goes also into the microphone. And if it goes into the microphone, the other side will hear whatever he's been saying, and there will be an echo that will continue and go on, and that's not a way to handle a conversation. An acoustic echo canceller takes that data that comes out of the speaker and subtracts it from what goes from the microphone into the encoder. So what we encode doesn't include what we played back locally. Okay? And if we look now at the diagram that we have somewhere around here, what you'll notice is that we take the data from the speaker and subtract it before we go into the encoder. So that was acoustic echo canceller. Now let's see the other three lesser known algorithms. The first one is going to be automatic gain control. With automatic gain control, what we're trying to achieve is to make sure that the volume level of the audio is going to be uniform or average across the whole session. Why do we need that? The first reason is that the user might be in a different distance from the speaker at different times. I can talk directly to the speaker or try to talk somewhere else, and then the volume changes within the actual audio that is being received and listened to on the other end. It doesn't matter in this type of microphone, but if we use, for example, an external microphone, or I'm standing near or far from the microphone that is inside the camera, or if this is a room system and there are multiple people in the room, each one in a different distance from the microphone, I don't want the levels of the audio that they have to be different for the person on the other end, because that is going to make the conversation a lot harder to handle. This is why most voice over IP systems today will have an AGC, an automatic gain control algorithm inside the actual code. Where do we place that? Right there next to the microphone. We look at everything that goes from the microphone before it gets into the encoder, and we level it out so that we've got the same volume level across everything. It also means one more thing. If you try to play with the volume level of the microphone, it's not going to help you, because WebRTC in the browser is going to disable that or level that up again to where it wants it to be. So volume level playing with WebRTC happens on the receiver end, not on the sender end. The second algorithm I want to talk about today is VAD, volume activity detection. VAD tries to check when someone is speaking and there is some volume and information that needs to be captured and sent versus where nothing is being said. At that point in time, VAD will mark that part of the conversation as a place that there was silence in. So it checks for voice activity detection. It checks when there is voice. With voice over IP and with WebRTC, when we talk about VAD, we assume a VAD that takes place locally and usually within the encoder itself. The purpose of using a VAD is to understand when we need to send actual audio, and then we compress the audio using audio-related algorithms, versus when there is nothing to send. And if there is nothing to send, we can send an indication that there is nothing, and that is going to cost us less in CPU and in bitrate across the network. And since this is a conversation, either I'm speaking or someone else, there are going to be long periods of time that there is going to be silence. And that silence doesn't cost us as much as actual audio that is being sent. Why? Because we're using VAD to capture and understand that. The other techniques in VAD or uses for VAD, for example, in turn detection for voice AI, we're not going to get into that in this specific video. Where is VAD placed? Usually next to the encoder or inside the encoder itself. The encoder itself has a VAD algorithm or component that knows what types of frames to generate from the encoded data, from the data that we received and encoded on the other end. The third and last algorithm I want to talk about is CNG, comfort noise generation. We had VAD that says there is nothing to send, and then there is CNG that says, well, if there is nothing to send, let's still play out something nice to the user. What does that mean? If you listen out to this, you're probably hearing a lot of things around. People moving around, just, birds, noise of the wind or whatever. In many cases, this is white noise. There is some noise level that is there at all times. If you go into a recording room, for example, facility, or to a very high level theater, you might listen and see that there is nothing in there. Why? Because even the walls are going to be noise suppressed and they're going to capture the sound that bounces through them. It actually hurts the ear a bit, and it's not that nice and natural to the hearing, which is why when there is nothing to send or when nothing is received, it is better for us to actually play some kind of a white noise, a comfort noise to the user that is listening in. And this is where comfort noise generation comes in. It simply does that on the receiver end as part of the decoding process, either after the decoding or a generic part of the decoding. Why else is this important? Because we're going to use that when we listen to understand if we got disconnected, if there is no visual cue and if we're not looking at something to know that things are disconnected. When we're disconnected, we immediately know because there is no sound. Remember that time when you listened to the phone, you understood that there's no one there and you checked to see and you saw that it's still ongoing and then you continued waiting? That's because there was no white noise in there, no comfort noise that was generated. Okay, so we had actually four algorithms that we're going to use for audio processing in WebRTC and also other voice over IP protocols. My name is Levent-Levi, and if you want to follow the work that I do, go check on bloggeek.me. There are a lot of articles there, as well as additional videos and educational material around WebRTC. Thank you.